And welcome back to the afternoon session of our conference on predictability in general relativity, which is being organized to honor Professor Ivan Choque-Bruja for her seminal contributions in the field of mathematical relativity. And our next speaker is Cécile Junio, who is a researcher at École Polytechnique, and she is going to present before us her work on stability of Kaluza-Klein spacetime. So, Cecile, over to you.
Thank you very much. So first, I would like to thank the organizer for inviting me to talk in this conference. So the work I will present today on the stability of the Kaluza-Klein spacetime is a work in collaboration with Anna-Laura Stingo from École Polytechnique and Zoe Wyatt from Cambridge University. So in general relativity, the spacetime is described by a Lorentzian manifold, which is usually a four-dimensional manifold, and which is equipped with the Lorentzian metric, which is the data on each point of the spacetime of a quadratic form of signature -1, 1, 1, 1. Einstein equation says how the spacetime is curved in presence of matter, and they can be written r mu nu minus 1/2 of r g mu nu equal t mu nu, where r mu nu is a Ricci tensor. It's a second order nonlinear operator on the metric. R is a scalar curvature. It is a trace of the Ricci tensor. G mu nu is a metric, and T mu nu is the energy impulsion tensor, and its form depends on the matter model which is under study, and we will see examples afterwards. So this system of equation, this is a system of equation because the index mu and u are taken between 0 and 3 if we are in 4 dimensions. But really, at the beginning of the history of general relativity, there have been the idea of considering higher dimensional spacetime. So the first one to have this idea were Kaluza and Klein in 21 and 26. And they consider a 5-dimensional Lorentzian manifold, which is symmetric in the additional direction. And later on, they say that this direction could be compactified, and thus they consider a manifold of the form M times U1, where M is a 3 + 1 dimensional manifold. So a metric on M cross U1 can be written without loss of generality under the form G alpha beta, dx alpha, dx beta, where, so this is metric which is a Lorentzian metric. This is Lorentzian on M. P is a scalar function on M, and A alpha, dx alpha is a one form on M. And being symmetric in the U1 direction means that none of this quantity depends on the y coordinate. Now, Einstein vacuum equation for the 5-dimensional metric. So Einstein vacuum equation can be written just Ricci equal to 0. They are equivalent to a system of equation for the Lorentzian metric on M, P, and A, which in fact corresponds to Einstein-Maxwell scalar field equation with strange coupling. Because strange because it's not the one which usually appear in this kind of matter model. So more precisely, to see this, you have to introduce F alpha beta, which is an antisymmetric two-form D alpha A beta minus D beta A alpha, which is very reminiscent of the way you go from the electromagnetic potential to the Maxwell two-form. You take f equal logarithm of phi, and you do a conformal change of the metric. And for this new variable g tilde f, big F and small f, you obtain so Einstein equation for the metric G tilde with a right-hand side, which corresponds to so this is the energy impulsion tensor of a Maxwell field, plus this, which is the energy impulsion tensor of a scalar field. And for F, you have a wave equation with some quadratic term in F and in big F. And for E2F time F alpha beta, you have the Maxwell equation. So there is a trivial solution to this problem, which is Minkowski metric in R4 plus 1 compactified in one direction. In other words, this corresponds to this taken to be the Minkowski metric in R3 plus 1, phi equal 1, and A equals 0. Okay, so it's what the solution that I've written here. Okay, so this theory then was extended much later by Kerner in '68, and he considered this time a 4 plus D manifold, Lorentzian manifold, which is invariant under the action of a Lie group G of dimension D. And then the Einstein vacuum equation for the metric G tilde in 4 plus D are equivalent to Einstein-Yang-Mills equation in 4 dimensions, plus some scalar field in the same way than scalar field appeared in the previous reduction. Okay, so this trial, this attempt to add more dimension to the spacetime were for having an unification of the standard model with gravitation, and this Kaluza-Klein reduction as a later application in supergravity. And I just wanted to mention that it was a subject which was very important for Yvonne Choquet-Bruat. Even so in her memoir, she says that when she met Einstein, he asked her to work with him on the theory of unification, and at that time she did not want to. But later on, she wrote some paper on the causality of supergravity, and there is also a whole chapter on Kaluza-Klein reduction, which is that you can find in her book General Relativity. So if we want to consider a spacetime with more dimension, so then it's natural question to ask what happens if we don't assume anymore that there is symmetry in the additional direction. So to have some to get some intuition of what can happen, let's look at a simpler model. We just look at a simple metric on the product space, minus dt squared plus dx squared. What I mean by dx squared is, so minus dt squared plus dx squared is the Minkowski metric in R3 plus 1. So plus R squared dy squared, and consider just the wave equation, the linear wave equation on this manifold. Then it's natural to do a mode decomposition in the y coordinates, so to write phi as the sum of phi k e to I kp. And then the wave equation for phi gives an infinite system of Klein-Gordon equation for phi k with masses k squared over r squared. So for physical reason, it can be very natural to say that r is very small since we don't see the additional direction. But if r is very small and maybe at the smaller than Planck length, then the modes which are created are really too high energy to be something which can be measurable, and it's why they are not usually considered in physics. But they are mentioned, but not really considered. But we know that mathematically, even small, for a nonlinear problem, even a small perturbation can have an effect. And so the natural mathematical question, the first question, is the nonlinear stability of the trivial solution under non-symmetric perturbation. And so it is the result we prove with Anna-Laura Stingo and Zoe Wyatt. And I will give a more precise statement later on in the talk. So the setting to study the stability problem is the setting of the Cauchy problem, which was initiated with the seminal work of Yvonne Choquet-Bruat and Guéroche. And so you consider an initial data set, which is sigma G bar K, where sigma is a three-dimensional manifold equipped with the Lorentzian metric and a symmetric two-tensor. And this data correspond heuristically to the data, the shape of the space at time t equals 0. And the K is the speed of deformation of the space at time t equals 0. To find a solution to what is called a development of an initial data set is a manifold MG, such that sigma is an hypersurface of M, or there is an embedding of sigma into M. The restriction of the metric G to sigma is G bar, and K is the second fundamental form of the embedding of sigma into M. But if you don't know what is the second fundamental form, it is like the data of DTG at time t equals 0. The initial data cannot be chosen arbitrarily, because if we want the manifold MG to be solution to Einstein vacuum equation, then some of the equation, mainly R0I equals 0 and R00 minus 1/2 of RG00 equals 0, are equation, in fact, which can be expressed only in terms of G bar and K. And so they have to be satisfied by the initial data. And the theorem of Choquet-Bruat and Guéroche, which is mainly local well-posedness for Einstein equation, says that for every initial data set which is sufficiently smooth on the solution of the constraint equation, there is a unique maximal globally hyperbolic development solution of Einstein equation. So development is what I explained here. Maximal means that if there is another solution, they can be embedded, isometrically embedded in the maximal development. And globally hyperbolic means that if I take for every point in the space-time, every inextendable time-like curve will meet one and only one the hypersurface sigma. So this theorem, in fact, it's valid for a lot of, in fact, for our problem of on a product space R3 time U1. There is no assumption on the geometry of sigma to be able to prove the local well-posedness. But if you to have local well-posedness, the only things to do is to solve the constraint equation. And it's something I've done with Katerina Valcoux on a product space R3 time d-dimensional torus. So I will now give some references on the stability of Minkowski, because as I said, Choquet-Bruat theorem is only a local well-posedness result, and it doesn't say what the global the maximal globally hyperbolic development looks like, if it is geodesically complete or not, for instance. So stability of Minkowski means starting from initial data which are sufficiently close to the initial data for Minkowski, is there global existence of solution? Is the maximal globally hyperbolic development geodesically complete? So this has been solved in vacuum by Christodoulou and Kleinerman, and then there have been some extension by Lindblad and Rodyansky in wave coordinates, and I will talk a little about that afterward. And many, in fact, there are many more extension refinement of this theorem that I will not quote here. But for more precisely the subject of this talk, I want to mention a result also by Wyatt on the stability of Minkowski for Kaluza-Klein equation. This means, so this result is really to consider this system of equation and show stability of the trivial solution, which is the Minkowski metric phi equal 1 and A equals 0. And also, since, as I said, when we want to consider the non-symmetric perturbation, then we see Einstein, we see Klein-Gordon equation popping out. It's interesting to give some references for stability of Minkowski for Einstein-Klein-Gordon equation. So there have been some work by Le Floch and Ma, and then by Wang and Ionescu-Posader proving this result. And let me mention last reference on the last stability result, which is a recent result by Anderson, Blue, Wyatt, and Yao. And what they prove is the stability of the solution, so on which is the Minkowski metric plus K, where K is a Ricci-flat metric on a compact manifold. Because this Minkowski plus a Ricci-flat metric on the space on a space-like Ricci-flat metric is a particular solution to Einstein vacuum equation. And so in this result, they prove the stability when the dimension on Rn plus 1 is with n greater than 9 to be able to have n of decay to be quite comfortable. In the subject of references, it's also important to give some references on some wave and Klein-Gordon system. So we use many work in our paper, so work by Kleinerman and Katayama, Ozawa, Tsunagawa for Klein-Gordon equation, work by Anelinak for the wave equation, and for wave Klein-Gordon system, let me quote some result by Ma, Stingo, Kleinerman, Wang Yang, Wyatt. And there are also some results on product space by Ettinger, Metcalfe, Sodge, Stewart, etc. It's not exhaustive. So the strategy we follow for proving the stability is by using wave coordinates. So let me present what are wave coordinates, and it's also the strategy which is used in fact for proving local well-posedness by Yvonne Choquet-Bruat and Guéroche. And also it's used in several stability results, such as the result by Lindblad and Rodyansky, or the result by Wyatt and by Le Floch-Ma. So if you can write, you can always write the Ricci tensor in coordinates. It can be written under the form. So here are all the terms which involve two derivatives of G, and I put aside all the terms which are product of the one derivative of G. And the term which involve two derivatives of G there is one which is the D'Alembertian in the metric G of the metric coefficient G mu nu. And there are terms which can be written under this form, where H is a quantity which involves one derivative of G. And it turns out that this quantity is corresponds to the D'Alembertian in the metric G of the X row coordinate. Wave coordinates are coordinates which satisfy H row equals 0. So coordinates, in fact, which satisfy themselves a wave equation. And in this coordinate, so this term disappears, and the Einstein equation can be written as a system of quasi-linear wave equation for the metric coefficient G mu. And the strategy to solve Einstein equation is in wave coordinates is the following. So you start with physical initial data, which are G bar and K, solution of the constraint equation. So I recall that G bar is a Riemannian metric, and K is a symmetric two tensor on sigma. And from this physical initial data, we need to construct initial data G mu nu, dt G mu nu for the system of wave equation. Okay. So when mu and u are space indexed, you just take G to be equal to G bar to be coherent. G0, 0 and G0 I are free, and in order not to introduce problem, you can set G0, 0 equal -1 and G0 I equal 0. You set dtgij equal kaj, and dtg0, 0 and dtg0i, you choose them such that the wave coordinate condition is satisfied at t equals 0. Then you solve the system of wave equation, and you know that if the initial data are regular enough, you have at least local existence for such a system. And then the question you have to solve afterward is this metric you have constructed a solution to Einstein equation? And the response is yes, if we are able to prove that H rho is equal to 0 for all time. And in fact, using Bianchi identities on the Ricci tensor on this, you can propagate this condition. Okay. So I think now I'm ready to state more precisely our result. So I recall that we wanted to prove the stability of the metric of the Kaluza-Klein metric zeta, which is the Minkowski metric in 3 + 1 dimension plus dy squared, and this is a metric on R3 + 1 time S1. Okay. So we want to prove, so we consider perturbation of this metric. So we write the metric under the form zeta plus h, where h is the perturbation. And in fact, since we need the initial data to be solution of the constraint equation, this lead to the, we cannot take initial data which decay as much as we want. There is a mass term which has to appear, m over r, because of the positive mass theorem. So this led us in the same as in the stability of Minkowski and as in the stability of Minkowski for Einstein vacuum equation or for Einstein-Clay-Gordon equation, to set H0, to write our perturbation under the form H0 plus H1, where H0 is envelopes the mass term. Okay, and H1 is allowed to have more decay. So our result is the following. So we consider initial data which for such that H1 is regular enough and have on decay more than 1, decay faster than 1 over r, then there exists a unique solution to Einstein vacuum equation with this initial data, which can decompose as the Kaluza-Klein metric plus H0 plus H1, and H1 decay almost as 1 over 1 plus T plus R, which correspond in fact to the decay. It's 1 over T plus R is the decay of a solution to the wave equation in 3 plus 1 dimension. Okay. So in the remaining of the talk, I want to give hints on the strategy to solve this problem. So the strategy is so with the vector field method. So let me recall you, explain to you what is the vector field method. So first, we need to look for vector field which commute with the wave operator on the product space. So the way this operator commutes with the translation in space on time, including translation in the y coordinate, in the compact direction. It also commutes with the rotation on the boost of R3 plus 1, but very importantly, it does not commute with the scaling vector field, which is T dt plus R dr. And so this property is very reminiscent, in fact, of the Klein-Gordon operator on R3 plus 1, which also commutes with translation, rotation, and boost, but not with the scaling vector field. And so the general method to prove global well-posedness with the vector field method consists in, is via a bootstrap argument. So we assume that until a time t, we have some energy estimate for our solution H when we are able to apply, when we apply a certain number of vector field.
Excuse me,
yes.
Cecile. So there's a question from Peter Kushil, Professor Kushil. What is the support of chi?
What is the support of?
Chi.
Chi, who is chi?
I think in a previous slide.
Chi, okay, we have this chi. So chi is supported for, so it's 1 for R greater than maybe than 1/2 is and 0 for R less than 1 less than 1/4. For instance, let me do a drawing. So I want this. So R is the modulus of X, so it does not involve the Y coordinate at all. And so this product is non-zero in this region, something like that. Okay. So it goes inside the light cone. It's important. We need the mass term. It's something important because we need the mass term around the light cone. It helps us to, for technical reason, it helps us. Okay.
Okay. Thank you very much. And
so the strategy, as I said, so it's the bootstrap argument. So we assume that we have energy estimate for ZIH, and via a Klein-Norman-Sobolev inequality, which is inequalities which give pointwise decays in terms of this kind of norm. We want to recover decay for the DH. So maybe let's assume that with this we are able to have a decay of the form C epsilon over T alpha. And then with this decay, we want to improve our L2 estimate using the energy estimate. So to prove energy estimate, we multiply the equation by dTH, and we integrate. We do integration by part. And what we need, we have, if for a simpler model, which is an equation of this form, box H equal dH times dH, we need to estimate. So dH squared in L2, and integrate this between 0 and T. And with what we have done, with our assumption on the Kleiner-Sobolev inequality, this is less than 1 integral from 0 to T of 1 over T alpha times epsilon squared. And we are done if alpha is strictly greater than 1, then there is global existence. Otherwise, we have some work to do, and it is the case, in fact, for Einstein equation, because the decay of a solution to the wave equation cannot be more than 1 over T. So with this kind of argument, we don't have global existence. So this problem, in fact, is very old, and it has been solved for the stability of Minkowski. And it's also present in our work, and we need to emphasize that there is some structure in Einstein equation which allow to deal with this weak decay. And to do this, we have to introduce the good derivative. So which are the derivatives which are tangential to the light cone, dt plus dr and 1 over r time rotation. And for if H is a solution to the wave equation, TH has better decay. Since Einstein equations are quasi-linear, we have to deal with, so they are quasi-linear terms which do not have null structure, which means that they don't involve tangential. Each non-linear term which involves a tangential derivative has a better decay, so better than 1 over T, which is integrable. And so in the quasi-linear terms, there are terms which do not apparently have the null structure, which are the quasi-linear term HLL times dt minus dr squared of H. But in fact, they can be dealt with because thanks to the wave coordinate condition, which I recall gave a relation between different derivative of coefficient of the metric, we can show that the coefficient HLL has better behavior, has better decay. So in fact, this term have a structure. And for the semi-linear term, we can notice that there is a structure in the system. In fact, the only term which does not have a term with a null structure in the right-hand side is the D'Alembertian of H L bar L bar. But importantly, it's not H L bar which appear here. Okay. So at the end, in the stability of Minkowski, even for the classical result, there is a sharp decay 1 over T for derivative of good metric, good coefficient of metric. But for H L bar, which is a bad coefficient, there is only log T over T decay. So okay, this is classical, but it's also yeah, it's a method we use. But there is another things to deal with in this strategy is so this was the the issue of structure to deal with the fact that we have only 1 over T decay. So there is also the issue of proving Klein-Norman-Sobolev inequality, because the classical Klein-Norman-Sobolev inequality involve the boost vector field, and we don't have access to the boost here. And so this problem, in fact, has been solved for in the study of Einstein-Klein-Gordon equation, in fact, already also for the study of Klein-Gordon equation itself. And the idea is to perform estimate on hyperboloid, so which are a surface of equation t squared minus x squared equal s squared. And on this surface, there is a Sobolev inequality, which can be stated as f is less than c over t3 time zf in L2. So this in particular give a decay 1 over t3 for solution to Klein-Gordon equation, but be careful, it does not give even at first sight you might think so, it does not give a decay 1 over t3 for a solution to the wave equation. It gives a result because for a solution to the wave equation, you don't have access to the L2 norm of all these guys. You have the L2 norm of a derivative of Z3F, or not Z3F. And so for the wave equation, it gives the same result as the classical Klein-Norman-Sobolev inequality. And so the foliation by hyperboloid, it's something we can do in the interior region. So for T greater than R, we can, instead of foliating the space-time by constant T surface, we foliate it by hyperboloid. Okay. And in the exterior, we have to do something else, but in fact, the exterior is not a hard region, because we can do we can perform a weighted energy estimate, which means that we it's energy estimate that we obtain by multiplying our wave equation by this kind of way with beta strictly positive. So you do this, you multiply a wave equation by the weight times dTF. You integrate on the space-time, you do integration by part. So this gives you conservation of this kind of weighted energy. And in fact, with this weighted energy, we can recover some pointwise decay in this form, which gives at least in fact the 1 over T decay that is expected for the solution to the wave equation. And this does not involve the boost in the scaling. In fact, it's the Z here can be taken to be just the rotation vector field. And moreover, when you do so, when you do integration by part, if the derivative fall on the weight, this gives you additional term with a good sign, which gives, in fact, integrated L2 estimate for the tangential derivative, and including the dy derivative. Okay. So it is how we can recover pointwise decay for our solution. But in fact, so we need, if we need to be a little more precise than that. We cannot just stay at this level. And to be more precise, the main idea of our work is to do a decomposition of our solution into a part which is the mean value along, well, sometimes it's T, sometimes it's S1, but along the compact direction. And so it's H flat, and H natural is the difference between the H and the mean value. And what happened is that H natural has a Klein-Gordon behavior, because first, because we have, for instance, in the exterior region, we see that we have better estimate for dy H, and with a Poincaré inequality, we can recover better better decay for H natural itself. So in the exterior, it means that we have integrated decay estimate, and in the interior, with the Kleinerman-Sobolev inequality, we have 1/T3½ decay for H natural, and it is the same decay as for Klein-Gordon. And in fact, we can have even improved decay using the L-infinity estimate, which are the same, which are adaptation of the L-infinity estimate for Klein-Gordon, which allow to really have a sharp decay 1/T3½ with the Kleinerman-Sobolev inequality. If we have some logarithmic loss on the energy, it transfers to the pointwise decay, but we have to improve this with L-infinity estimate. And H flat satisfies the wave equation. To see this, we just integrate all the equation with respect to on the torus, on the term involving the dy derivative disappear. And so it has the property that of a solution to the wave equation. So it has less decay in 1/T, but we can have the property that when you take derivative, you have a better decay in terms of the distance to the light point. And also we can perform an infinity estimate for a solution to a wave equation to have a sharp, better decay in 1/T1 minus a small thing. And if there is one thing to remember for the talk, it's the following, is that in fact there is a natural structure in this decomposition, which is because so the equation for H natural, H flat is taken by taking the mean in T. So in this equation, there cannot be product of H flat times H natural. So it's it can be a product of H. To produce a zero mode, you can multiply two non-zero mode or two zero mode. You cannot multiply a zero mode times a non-zero mode, because otherwise it creates a non-zero mode. And in the equation for H natural, so to produce a non-zero mode, you can multiply two non-zero mode, or you can multiply a non-zero mode times a zero mode. But if you multiply two zero mode, then you create a zero mode, so there is no such term. And in fact, what is funny in some sense is that this structure, in fact, is the same as the structure you have in Einstein-Klein-Gordon system. Because Einstein-Klein-Gordon system, you have a Klein-Gordon equation for phi, for instance. So you have quasi-linear term which involves the metric g times 2 derivative of phi plus m square phi equals 0. So you see that you have so phi is a Klein-Gordon, so it's like a non-zero mode, and for this, no, there is a difference that there is no product of phi in this equation, but you have the metric times phi, and the metric which satisfies wave equation or not Klein-Gordon equation. You have product of G and product of phi, because this is the energy impulsion tensor of a Klein-Gordon field, which gives that. So for this part, you see that there is the same structure, in fact, in these two equations, except that there is additional term in our problem, but these are terms which are very, very nice terms. Okay. So let's in the let me describe now a little, since there is a little time left, what is the principal difficulty in the Klein-Gordon coupling and in our problem. So since the difficulty I will present now is also in Klein-Gordon, in Einstein Klein-Gordon system, let me keep the notation of that I've just introduced here. And so the difficulty comes when you commute your Klein-Gordon equation with a higher number of vector field you consider. So E plus M phi equals 0. So when you do so, you need to control the L2 norm of Zng times 2 derivative of phi in L2. So if phi is the solution to the Klein-Gordon equation, its decay is not better than 1 over 3/3 Okay. And then if G is a solution to the wave equation, we don't have access to estimate for this. We only have access to L2 estimate for a derivative of this. So we need to use a RD inequality to be able to improve the decay, to be able to control something. And to do the RD inequality, we need to spare 1 over t factor of the 1 over t3/2. And in fact, all that this argument is, so as I said, it's for also for Einstein Klein-Gordon equation, and it's also it's the argument done in the work of Le Floch and Ma. So we have this. So this is bounded. Let's not consider we forget the log for the moment, because we have greater problem to deal with, because there is a 1 over t 1/2 here, which lead to, when we integrate this leads to a square root of t growth in the energy for phi. Okay. So this is a big growth, but in fact, it's not, it's okay to have this growth, because the problem would be if this growth would induce a growth in this term. But in fact, because of the structure, we see that on the equation for G, you have product of d phi. So when we want to consider this, we have product of this. And this, if we want to take it into L2 norm, there is one d phi which has the 1 over c3/2 decay. And the other one, the Zn d phi, if all the vector fields, for instance, fall into 1 phi, there is a square root of t growth. Okay, but this leads to a factor, a term which is of the form 1 over t, which is integrable. Okay, so this square root of t growth does not induce the square root of t growth in the energy for G. So it is okay. So there is a so this was as I said, present in Einstein Klein-Gordon equation. There is a small something specific to our problem is that in our problem we cannot do we cannot separate the energy between the non-zero mode and the zero mode at the higher level, because if I write the equation for the zero mode, it involves terms which are the integral of h times, so I integrate the quasi-linear term, and for h, so integrate over S1, And for the non-zero mode, I have the difference of the two. Minus Day01. Okay. And by doing so, in fact, it's something that I cannot do at the higher level because I lose the symmetric structure of the quasi-linear term by doing so. Okay. So this means that at the higher level, I have to assume that the L2 norm of H, the entire H, zero mode plus non-zero mode, has a square root of T gross. But in fact, the trick to go over this is to say, okay, I will assume this if I take two derivatives, okay? And if I take only one derivative, now I can separate between zero mode or non-zero mode because I can treat all these terms as a semi-linear term or not quasi-linear term. And this, the fact that I have assumed this is not a problem because if now I take one derivative Zn of my problematic term, which was my zero mode times two derivative of H natural, okay. This, if everything falls on H natural and H flat, so you have this plus term which are Z and H B times three derivative of H plus etc. plus other term. But this is a term that I can deal with because so this has 1 over T3 half decay in any case. 3 half. And this in L2, in fact, is something I can estimate in L2 straight away because this involves a derivative of solution to the wave equation. And this can be estimated as before with the RD inequality, which will make appear derivative of Z and H beta. But for this, okay, it is a level of regularity lower. So this can be assumed to be bounded. Okay. So I think that's all for today. Thank you for your attention.
Thank you very much, Cecile, for such a wonderful talk. So do we have any questions from the audience? No, I don't see any questions from the chat. So so I request all the participants, if they have any questions, they can write to
There is a hand raised.
Okay, so Sumati, yes, please.
Yeah, I'm taking advantage of my position as co-host to just ask a question directly. I think we have also one by Piotr. So I just wanted to understand a little bit better. I mean, this is a very technical talk and I'm not in the area.
Sumati, you're not audible. You muted yourself, I think.
Sorry, okay, I'm sorry. Yeah, so I wanted to ask what exactly, and this is not an area that I'm familiar with, but these weak null structures seem to be kind of important to this analysis. I wanted to understand in what sense are they weak? Is it in terms of at a topological level, or are they weak in a, I mean,
okay.
Right.
It's
just
weak it's weak in the sense that okay, so there is some coefficient for which there is term without, which does not involve good derivative on the right-hand side, and for which there is not, so the decay which is expected for a solution to the wave equation in 1 over t. So and here in this system, some terms have a weaker decay, which is log t over t, because there is no term with involving tangential derivative on the right-hand side.
Okay, so it doesn't affect the nature of the, I mean, this is to do with, I see, so it doesn't affect the nature of the geometry or any of this, but it's just in terms of you're talking about the weakness of the behavior of the perturbations, is that right?
It's really, in fact, it's really related to this system of equation in wave coordinates. By choosing other coordinates, you can have you can avoid logarithmic loss in the decay. But there is no really geometrical meaning at this point.
I see. Okay, thank you. I think we now have a question.
Hi, Peter.
Yes, hi. Hi, Cecile, can you hear me?
Yes.
Yes, good morning, everyone. First, a nice, beautiful talk, and thank you very much. Beautiful results too. Can you show your theorem again?
Yeah.
So let's see. Technically, so this is now in the dimensions. The space dimension is 3. So is it 3 plus 1 now, or?
It's so the space time is R3 plus 1 time S1.
Okay, great.
It can be so it can be generalized to R3 plus 1 time d-dimensional torus without changing anything.
Yeah, so that's what I was thinking, that probably by these techniques you can handle any flat torus as well.
Yes.
Now there is something I'm very confused about. This has to do about my question about the support of chi, and I think this already shows up in the Lindblad-Rodniansky paper. And other papers as well, right? Somehow this how is this Bondi mass decay compatible with this constant mass ADM? That's something which I understood once and I forgot now. Can you just comment on this, how this works?
Yeah, in fact, we the decay we obtain is not in this region is not precise enough to really make a difference in this asymptotic region between the mass term and the other term. Okay.
So your decaying term is actually I mean, this m over r term is swamped by the terms you have. You don't have a Bondi mass formula here.
No, we don't. There is no. It's certainly true, but not. Yeah, it's not apparent. These coordinates.
Because your chi, I was a little confused about it, but I think that your chi is 1 includes the light on the light cone, right? Is it, or?
Yeah, it's 1 on the on the conical neighborhood of the light cone, because in fact
exactly right. Yeah.
Important
so it has to go beyond.
That the T equal R surface, we want it to be space-like, so that we can it's easy to separate between exterior and interior for technical reason. Okay.
So can you also comment why so Anderson, Zoe, and friends they didn't get as far as you could? Where does this show up? Where is the main technical improvement?
So there is two. So in the results, I think they don't really try to optimize.
Well, I'm sure they tried. I'm sure they tried.
Because they did not do the separation into
the torus.
Into
the constant.
They didn't do this separation, but I certainly don't claim that I can that we can do the same result as with a general Ricci flat metric. because then in that case we lose this decomposition.
So this is essentially some kind of product Fourier structure, which is important here. Which, so if you had some control of this kind, then probably one should be able
if we are able to have the same kind of structure, then I guess with some work it can be adapted. But in general, there is not such a decomposition, not as I'm aware of.
Now, there's this folklore knowledge that if you are in, if the space-time, so not Kaluza-Klein part is higher dimensional, that things are easier, and then you don't have to do this. In other words, if you are on R1 plus n plus a torus, this would go through immediately without difficulties, or?
It's easier because then you have more decay because there is more dimensions, there is more decay, and you don't really need to look so carefully at the structure.
I mean, it would be nice that you know, somebody writes down a clean statement about it, because somehow it's just hanging in the literature. So if you can do it in higher dimensions, maybe you could add a little comment about this, making precise that how things work. Let's see, I had another question. Let's see. Well, I forgot. Oh, yes, right. So you had this, at some stage you had, you said, let's forget about the log terms because they're less difficult, but still you've ended up with an integral in 1 over t at some stage, right? So, which produces logs, right?
Yeah.
So how do you handle that?
So in fact, so all this part is very, so it's quite technical, and it's in fact very similar to the proof of stability of Minkowski for Einstein-Klein-Gordon by Lefloc-Ma. So mainly the same strategy, and you have to at some point. So it's why we use, for instance, L infinity estimates to so at some point the log loss does not fall into so it's okay to have a logarithmic loss as it does not goes into the L infinity estimate. If I have log of t and 1 over t, it's okay. It's linearly it's linear. But if I have log of t times log of t over t, then
okay,
it's not good. But
so there's a way of technically.
Why there is an infinity estimate, but it's a lot of work in fact.
Thank you very much. Thank you very much. Beautiful talk. Thanks.
Sumati, do you have any question?
Yeah, just a very general question, but I mean, from a non-expert, I mean, somebody who doesn't really know these proofs. You know, we do know, however, that Kaluza-Klein, you know, the black hole in Kaluza-Klein has instability, the statements of Gregory-Flamm instability. And so there's been a lot of sort of work around that and so on. You're, of course, dealing with flat Minkowski with a circle and looking at that particular geometry. I'm curious whether these modes that you're you know, the requirement of the modes, are they, in some sense, if you just compared with the kinds of modes that grow in the Gregory-Flamm, is there any way to compare them, any sort of meaningful covariant way of comparing them? But also to say, well, somehow those modes or the way that they grow is going to be different from your requirements here. I'm just curious whether there's physical constraints that these requirements on decay impose. I don't know if my question is clear enough, but hopefully something is.
I think really the problem is very different in the black hole context, because first the first thing that so there is this as you say there is this Gregory-Flamm instability, but in fact even if we wanted to try the same thing that we do but for stability of the Schwarzschild plus Schwarzschild metric plus dy squared, okay, is also a solution to ancient vacuum equation. And if we wanted to do the same, then we will have to study some Klein-Gordon equation on Schwarzschild. In fact, the decay is really not as good for this as first. Very few things are known, and it's very recent, and it's not the team as good as in Minkowski spacetime. So.
Thank you. Thanks. Yeah, I was just curious whether you'd thought about it, and maybe, even if it's a hand-waving kind of understanding of that. I understand, of course, that they're totally different space-times, and at some level, the mathematics must be completely different. So, but thank you. Thanks. Yeah.
Any other question? So I have a question, Cecil. So from a naive question from the point of view of computational relativist. So in your decay rates of the solutions of Klein-Gordon equations or Klein-Gordon coupling, so you showed the decay rate to be like one by T⁻3², right?
Yeah.
So is this towards the null direction or the time direction? Like future null,
the decay of 1/T3½ for the.
Yeah, that's true.
No, it's in every direction.
It's in null direction.
No, for every direction there is for the Klein-Gordon mode,
Okay.
there is 1/T3½ decay. And if you take really derivative which are tangential to the hyperboloid, you have even more decay, in fact. But,
okay, and does it also depend on the choice of initial data, like what kind of decay along the spatial direction and null direction we are taking in the initial data as well, or?
I guess if you take initial data which are very weak decay, you may not recover as much decay. But I don't know.
Okay. Good. Thank you very much. So any other question? So I don't see any other questions in the chat as well. So if there are no further questions, let's thank the speaker once again. And our next speaker is Professor Juan Antonio Valente Carun. So, but we have time for the next talk. So Juan, are you around?
Yes, I am.
Hi, good to see you.
Yes. Hello. Hi. Nice to see you again. So just let me see. Hi, Piotr. The things I'm joining also with the iPad. Let me see if it works.
It's okay. You have 8 minutes. You can try as many things as you like.
Yes. Okay, so let me see. And yeah, it's working. Okay, fine, perfect. So, very good.
Perfect.
Yes, I'm doing this with 2 computers, right? Because then with the iPad I actually can use a pointer. So right, okay. So it seems to be working. So that's really right.
Can you test your pointer and scrolling your slides?
Yeah. Yes, it's working. So yeah.
So yeah, I can see your slides changing, but I cannot see your pointer or cursor.
Let me see. Can you see it now? Yeah.
Oh yeah, some red dot blinking. Yeah.
Yes. That's right. Okay. Fantastic.
Yeah, sure. So we have 7 more minutes. If I mean, if you want to have some tea or coffee, feel free.
Okay, it's all right. I can. I think I'm ready to
Okay.
go for this.
The same applies to all the participants also.
Juan, you are in Vienna now?
Yes,
Yeah,
indeed.
it looks like. Yeah, I'm
Yes,
sorry.
yes. I am. Yeah, this is my Vienna week. So
Yeah.
yes,
Okay.
so not very far away.
So regards to Christiane.
Well, I think she's spending the whole day at the has a long day at the university today,
Okay.
apparently. Yes. So Mark Mars is giving a talk, I think, in 2 weeks, I think, right?
Yes, right. He'll be. Will you still be in Vienna by then, or?
I think I am that week, at least couple of
Okay,
days.
great, because he'll be in for the week.
All right,
So-
all right. So I make sure to drop by.
Okay,
Yes.
good. Well, I'll be back essentially in about 10 days only, so just before he comes. So
Okay.
I think we could start.
Okay.
I mean,
Um,
it's a couple of minutes, but Shalab, what do you think? Maybe he's gone for tea.
Yes.
We should wait exactly 2 minutes more or a minute longer. Okay, I think we can start.
Okay.
Thank you so much for agreeing to talk at our meeting. We're really pleased that you could make it. You sent us, you were the first one to accept and to send us your entire abstract and title. So thank you very much. It made the job as an organizer very much easier.
Okay. Thank you very much, Matti, for the invitations. It's a pleasure to talk today. So what I want to do today is do a sort of part review and part talking some new results. Well, and it's particularly an honor to talk in this event in honor of Yvonne Choquet-Guard, who has had a big influence in a lot of the things that I'm going to talk about. It's not necessarily direct influence, but certainly in spirit and in philosophy. So yeah, so I want to start giving a light overview of the talk so that you know what I'm going to discuss. And I think that there is a big theme today, which is to discuss the relation between the asymptotic behavior of the gravitational field at null infinity and spatial infinity. So this has various names or in the literature, and I have chosen to call it for today the problem of spatial infinity. And for the other, and this is very closely tied to seminal work by Penrose, ideas of how to describe isolated systems in general relativity, and then Penrose had some conditions that were aimed at characterizing the systems, and then, well, it has turned out that they are generally very restrictive to describe generic spacetime. Nevertheless, they have been highly influential in the field and have driven a lot of our research. And then there's another tool, which is a certain approach to Penrose's point of view, so a conformal approach to study spatial infinity by Helmut Friedrich, and which I claim to give you a proper way or to provide a full understanding of the relation between Cauchy data, the initial value problem, relativity, and the asymptotic behavior rotational field. And then the claim is that ultimately this could actually help to settle down the problem of spatial infinity. And so this is very general, high level, but then I also want to show you how these ideas can be used to the computation of asymptotic charges. So this is a topic that has been of great interest in recent years. Right. So, but then before starting, as I already mentioned, so there is a theoretical underpinning here, which is due to Yvon Choquet, and is basically the formulation of the initial value problem in general relativity. So right, there's so more than so almost 70 years old result, right? That you can consult online the paper. But then I guess if you want to learn more about Yvon Choquet's point of view on relativity, I think probably the best way is to read her volume published by Oxford University Press some 14, 15 years ago. So this is really a treasure. There is plenty of things there, also sort of unexpected results and things to learn there. So I think should encourage everybody who hasn't seen this book, to browse it, right? So there's always something to learn there. Okay, so as I said, so there is a bit of introduction today and an overview. And so I want to talk about what John Stewart called in his book on advanced relativity, also a very recommended book to learn certain perspective on relativity. He called this asymptotic, and basically it's a name to the study of the asymptotics of the gravitational field, right? And well, so this is a topic that has been on and off in popularity, right? But then somehow I think in recent years has had some renewed interest, and for reasons that I will discuss later. And in any case, so what I want to say is that anybody who has been in the field for some time, so there is in fact a vast literature on the asymptotic rotational field. This is really extensive, covering 4 or 5 decades, even more, in fact, of work with different approaches, perspectives. But then there is some big chunk of this is really built on Penrose's characterization of isolated systems in relativity using the notion of asymptotic simplicity. And there is a point here, which I want to stress, right, that most of it, right, is formal in the sense that it makes assumptions about space-time, so to work, and this is fine, right? The only thing that one has to be very careful, so these assumptions may or may not be generic, right? So one has to be careful with this point. And indeed, trying to understand these assumptions, right, that arise on and on the asymptotics, on asymptotia, have kept several generations. So mathematical relativists busy. And again, so really the starting point of this was really given by Yvon Choquet and her formulation of the initial value problem. So this is somehow, I think, a preferred approach, or I think it would be the preferred approach to try to understand so what is the genericity of these assumptions, right, that are made in the study of asymptotics. And so I listed here some people, right, who have contributed, so different streams. So this is not meant to be comprehensive, right? But and I would claim that there has been actually quite a substantial progress, right, in recent years trying to understand the thing. But I think that there are certain bits and pieces here and there, and that need still to be clarified. And I will also try to discuss what pieces are missing here in my own opinion. Okay. So as this is a talk on asymptotics, so I have to give also some historical context, and I really, so from my point of view, I think the starting point is the definition by Roger Penrose, highly influential, of asymptotic simplicity. I'm sure most of you have seen this many times. And so I will not now go into the details of the definition, right? But then basically you say that space-time is asymptotically simple if that meets a complex conformal extension at null-infinity, which is similar to that of the Minkowski space-time. And key to this definition is the notion or the statement that this extension has to be smooth, right? So there are also other versions of this definition, right, where the regularity is relaxed, so you require a certain number of derivatives. So say you call it a k asymptotically simple, right? If the extension has ck, so k the derivatives and so on. Okay, so but then I keep, but of course, so I think the ideal setting where, and I think in terms of original formulations, right, so he really was thinking of working on a smooth setting, right? So what was the purpose of this definition, right? Well, so the definition is to provide a geometric framework to study the asymptotics of gravitational field. So this is really the leading idea behind. And so then attached to this, so that there is a it allows, so this geometric point of view allows to translate the smoothness, right, of a conformal boundary to so one calls the decay of the field, say what is we call peeling, in terms of smoothness statements about the conformal boundary, right? And then a sort of corollary of this idea, right, or leading principle, is that if you are a setting where the smoothness of the boundary, of the conformal boundary subscribed null infinity is restricted, right? Then you have some sort of a different type of decay. So this is somehow the general guiding principle. Okay, so also again, just to be on the same footing, so I just want to, so I already mentioned this idea of peeling, right? And so this is an observation or a result that goes really back to the original work by Bondi and collaborator Sachs on the asymptotic gravitational field in the early 60s, and then was put in a more geometric footing by or shaped by Penrose. And so what is this? So basically, if you have a asymptotically simple space-time, right? So assuming that the extension is smooth, then the Weyl tensor has a hierarchical decay, right? So there is a component psi4, which one associates to the radiation field, right? Which is the one that is slowly decaying. And then as you move through these various components of the Weyl tensor, so then say, for example, you reach the Coulomb component, so which goes like 1 over r cubed, when r is some suitable parameter along generators of light outgoing light tones, then you have r4, and then you have the fastest decaying component psi0, which goes like 1 over r to the fifth, right? So in this result, right? So the smoothness of the conformal boundary is key, and in fact, so it's true that one actually doesn't need smoothness here, right? So that there is one can make the count and then just bookkeeping and then allow them to know which is the minimum amount, right, of derivatives to guarantee this, right? But then if you are somehow below that threshold, then some of the decays or some of the components may actually change. Okay, so I mean, so given this definition of asymptotic simplicity, so there are some natural questions which, well, again, and I think this is somehow what I think the influence of Yvonne Choquet is that one would like to address these questions of genericity through initial value problems. Right? So one would like to construct a space-time which are asymptotically simple. Right? So then a first question is how large is this class of space-times, right? So one would like to know, so what is the prescription? So what are the initial data that you should prescribe on a free manifold, so the pre-metric and curvature, so that the resulting space-time is asymptotically simple. okay, for example, and so once you know what the recipe is, yeah, so you like to know whether, well, so this is so this class of space of data is something like an open set, right, in the space of data for the Einstein equations, right, or just corresponds to isolated points. So what is happening here, right? So this sort of things, and then the natural way to address these questions, as I said, is through the initial value problem. Okay, so now, so if you take this point of view and then you want to formulate an initial value problem to try to address this point, so then there is a technical difficulty, right? And then this is really what is at the core of this problem of spatial infinity, something that was actually first observed in the literature by Penrose, is that whenever you have vanishing, so a non-vanishing mass in the space-time, then at spatial infinity, so the point at spatial infinity, which in Minkowski is completely regular, so for a space-time with a mass, you have a singularity somehow. It's a singularity in the conformal structure, right? So it's to say that the conformal structure at the point of spatial infinity is singular. And then, so you can, as a natural way of thinking of this, is you have, say, the Penrose diagram of your like Minkowski type, like space-time, and then you have the singularity somehow as being something akin to a negative mass Schwarzschild singularity, right? So negative singularity, right? Of course, so this singularity is somehow, at least in this picture, right, causally disconnected, right, to the rest of the spacetime, but then doesn't mean that you may not actually experience the effects of this singularity inside the spacetime, right? So just to say that, so because I will be using also this sort of diagrams, right? So another point of view is well, you have your initial hypersurface and you have obtained a point compactification of this initial hypersurface. So then the sky somehow emanates, right, from spatial infinity, right? So the space-time, so this region here is in fact the stereo of the cone, right? And then the region inside the cone is this region here. Okay. So then, so there have been some attempts, right, to so the first attempts, say, to try to construct spacetimes which are asymptotic simple, so that they back to the work of Helmut Friedrich in the 80s, and then well, sort of somehow realizing that there is a technical problem with the dealing with spatial infinity, somehow he tried to avoid this by constructing spacetime by prescribing information on an hyperboloid. That's to say, some space like a surface that is asymptotically null and reaches to the conformal boundary, so to a future null in infinity. Okay, and so this result was the following, right? So you prescribe some initial data, hyperboloidal initial data, which is somehow close to data for the hyperboloidal data for the Minkowski spacetime. If you do that, right, and the data is sufficiently small, then you can recover the region, somehow the future development, right? And you can recover everything that is to the future of this diagram, right? And then so resulting spacetime will have a global structure which is similar to that of the Minkowski spacetime. And in particular, if you somehow concoct your data not only to be small, but satisfy certain regularity conditions here at the intersection with null infinity, then somehow the result of spacetime is so the conformal boundary is actually smooth. Okay, so this is something that you can do. Of course, this is not completely satisfactory, of course, because this is semi-global in the sense that if you want now to evolve towards the past, so you cannot recover this region here, right? So you cannot recover the whole of the space-time, right? So somehow you like to be able to push down this hyperboloid down to a surface that hits spatial infinity. And then as this is also, again, in honor of Yvonne Chouquet, so I want to mention a historical remark. So that this approach to proving somehow global stability of space-time through making use of conformal methods actually has a precedent in the work by Yvonne Choquette, and actually I forgot the other author, and Dimitrios Christodoulou, so my apologies. So it's Yvonne Choquette and Christodoulou, and what they did here is they studied the global system of solutions to the Yang-Mills equations and some other fields, so the Higgs field and some spinorial fields. So this is a work from 1981. And then what they do there is they observe that this Yang-Mills equation and the Higgs fields, they are conformally invariant. And then, so instead of studying these fields on the Minkowski spacetime, they study them on the Einstein cylinder, right? And then basically through this observation and using Cauchy stability, so that they actually can show that if the data for this Yang-Mills field is small enough, right, then it will cover a portion, a slab in the Einstein cylinder that contains somehow the Minkowski spacetime, right? So this is really a precursor of Ernst Friedrich's approach to construct spacetimes through conformal field equations, of which I will say something more later on. Well, so the first global stability result for the Minkowski spacetime, which includes spatial infinity, is due to Christodoulou and Kleinerman. So I think Cecile, who know, already mentioned this, right? Again, so what is the idea here? So you prescribe now Cauchy data, right? Which is in some sense close to the data for the Minkowski spacetime, right? With certain assumptions about the decay of this field spatial infinity, and then they are able to recover spacetimes, right, which have the global structure of Minkowski spacetime. So they are also basically complete, right? However, when they look at the behavior of the gravitational field in the spacetime at non-infinity, so they are not able to recover the Peeling behavior established predicted by Penrose. Okay, so this in other words, so then the conformal boundary, right, in this spacetime seems not to reach the threshold of regularity that you would require to deduce the Peeling behavior. And so at the time, while it was not clear whether this was a technical problem or there was some fundamental issue here, right? So it could be that, right, if you went through the estimates and the calculations, you do them with more care, so they may be able to recover Peeling. So it was not clear. I think this point, so this point has now been settled, right? So that there is indeed a fundamental problem here, right? And I will go through that in slides. Well, so there is a trick or a way to generate spacetimes which have indeed a smooth non-infinity, and then this is a trick due to Piotr Krusher and Ervan Delay, and this is really working on the work of Corvino and Schoen on gluing techniques, right? So these gluing techniques, what they do, they allow to glue some, say, asymptotically flat initial data to some arbitrary exterior, right? So, and then in particular, so you can take some initial data for the Einstein equations, which is arbitrarily small, say close to Minkowski data, and then this can be glued to an exterior region corresponds to the Schwarzschild spacetime, right? And then there is in between some transition region, right? And then the point of this construction is that then you have a spacetime whose behavior, right, because of causality, domain dependence arguments. So the behavior near spatial infinity is very well controlled. In fact, you know that this data for the Schwarzschild spacetime, right? And then in this region, so you can pass an hyperboloid which starts somehow in your initial in this blue region where you have your arbitrary initial data, and then it enters the Schwarzschild region of the space-time, right? So then you have a whole hyperboloid there, and then if the size of your data is small, and this can be controlled, then so you will have perturbations of the Minkowski space-time arising from here, and then you can make use of Friedrich's semi-global resistance result, right? So then I guess so. This shows that there are indeed large classes of space-time which are asymptotically simple, right? Of course, the question is whether you want whether it's the generic behavior or not, right? Or whether you can have things that are maybe not so contrived as the ones shown by this example. Okay, so this, well, I mean, leads to I think the main point of this talk. So which is that you would like to understand much better. So what is happening at spatial infinity, right? And then, so this is something that Helmut Friedrich has devoted a lot of time thinking about. And then to this end, he obtained or constructed a representation of a spatial infinity, which allowed the formulation of what he called a regular asymptotic initial value problem, right? So it's to say that he writes some initial value problem for some conformal equations, which are related to the Einstein equations. And these equations have the property that the data and the equations themselves are actually regular, both at spatial infinity and null infinity, right? So with this initial value problem, then he can actually then study what are the equations, so the consequences of making certain type of assumptions on the initial data, right? And then look at what happens somehow at Scribe. And so the principal idea, or main idea behind this construction is something that has been around in the literature for a number of years, and then, at least as far as I'm aware, can actually trace back to in some form to the work of Ashtekar and Hansen in the 70s, where there was this idea of giving a unified description of spatial null in infinity, right? So I think, of course, somehow the perspective or the point of view or the focus on the work by Ashtekar and Hansen was somehow different, right, to the later work by Helmut Friedrich. And then I should also mention the work by Robert Weig and Bernd Schmidt, right, where they also analyze, so make use of this Ashtekar-Hansen hyperboloid, and then see how this hyperboloid combines with the evolution equations of general relativity. Okay, so the basic idea, I mean, so the geometric setting. So I don't want to spend too much time on this, but just you get an impression, right? So you have, what you want to do is to describe this region of space-time, so the neighborhood of spatial infinity. And the way one proceeds is that one makes a blow-up of the point at spatial infinity, so that instead of being a point, it becomes a sphere, a two-sphere, right? And then, so you also allow space on the spatial dimension. So basically, you can think about boosts, which are described by this time direction, and then so you're transforming this point into a sort of cylinder, right? And this cylinder of spatial infinity has some endpoints, which I denote I plus and I minus, call it critical points, and these points are described the intersection of spatial infinity with null in infinity, right? There's a sort of caustic set, if you want, and right. So then I will make using of this diagram here, which is, as I stated, is not a conformal diagram, right? It's a really a coordinate diagram, right? So in Penrose diagram, null hypersurfaces are always drawn at 45 degrees. So in this case, right, somehow the coordinate that one is using, which are based on the use of certain conformal invariants called conformal geodesics. And so we use something that's called conformal Gauss gauge, right? So the details of this is not really very important at this stage, right? But then, yes, so so you obtain this blow up of partial infinity, right? So the idea is that for some reason that I will explain later on, right? You have some information at the intersection of a spatial infinity with the initial hypersurface, that you are able to transport this information along the cylinder and see what happens at the intersection with null infinity, right? Both to the future and to the past. Right. So the key observation, and somehow this is the central observation, is that the cylinder happens to be a total characteristic of the conformal Einstein field equations. To say that you cannot prescribe boundary conditions, so boundary data on this cylinder, right? So in fact, all the evolution equations are reduced to transport equations on this cylinder. So, as I said, so therefore, if you have some information about your gravitational field here at the intersection of your initial hypersurface and the cylinder, this information can be evolved toward the future and both to the past, right? And then so this now in the technical jargon, so allows you to compute solution jets, right? So as to say some coefficients of a Taylor-like expansion around spatial infinity, right? To say that you were writing solutions which are formal expansions in some terms of some parameter, a rho which measure the distance from a spatial infinity, right? So then the coefficients of this Taylor expansion will be the components of these solution jets. And as I said, so these components can be actually computed explicitly right from the initial data. And somehow the point is that in particular, so particular focus in this type of expansion is to look at what happens at the coefficients of the components of the Weyl tensor. And these coefficients can be computed explicitly modulo some computational complexities. So you really need to exploit this. You really need to make use of computer algebra, otherwise you get bogged down very quickly, right? But then if somehow you have computer algebra at your service and you manage to debug it and make it run, then so that you find out that in general, right, for generic classes or large classes of data, then you find that these coefficients tend to have logarithmic divergences at the sets where these critical sets, right? So this is, I think, one of the key observations by Henus Friedrich, and then when I was a postdoc of Helmut, and then I also explored these further. So now, so these logarithms have a lot of structure. In fact, so one can actually fine-tune the data in such a way that to block out or cancel out the logs appearing in certain parts of expansions. So this is something that one can do. Yeah, somehow it's somehow a natural consequence of these calculations, right? And then, so that's the nice thing, right? So you can actually see what sort of behavior so what are the effects of certain pieces of the data in the expansions which describe the behavior at null infinity. Okay, and then to give you an idea of the sort of thing that one can do, so I want to mention some results that I obtained some years ago with a former student of mine, so Edgar Gasperin. And then here, what we were doing is we're assuming some initial data that admits a nice conformal extension near spatial infinity. So your data, so you can make a point compactification of this data, and we are actually assuming that the metric. So first of all, we assume that the data is time symmetric, right? So this is a simplification, right? But this already you get non-trivial results in this case. So even if you assume that the curvature is 0, and then you assume that the only remaining piece of free data, which is the conformal class. So you assume that you have a metric which is analytic. So that means analytic point extension, right? Point compactification at spatial infinity. So this seems to be very overly restrictive, right? But then what one finds is that you just take data satisfying this assumption, right? Analyticity, then you look at what the expansions at null infinity would be for the development of the space-time. So I have to say that these expansions are formal expansions, right? So there is a bit about how to tie to establish firmly that this behavior actually belongs to one tied to really a particular solution to the Einstein field equation, right? But assuming that you actually can evolve space-time long enough to compute these expansions, then you would get this behavior, right? So then you already see that even the Coulomb component is not satisfying the peeling behavior, right? And then, well, you can refine this, right? So say now, if you assume that your data is such that its cotton tensor, which is somehow measure the deviation from conformal flatness for the tree metric. So if this cotton tensor vanishes at spatial infinity, then you can recover peeling for the Coulomb component, and then you can go further, right? Start putting extra. So you observe that this condition is a condition at a point, right? It's an asymptotic condition. It's a condition at the point at infinity. Now you require that the derivatives, so trace-free derivatives at this point at infinity vanish as well, then you recover peeling for a further component, and then so the classic peeling behavior is obtained by actually requiring an extra condition on second derivatives of this cotton tensor. Okay, so this already I think fit very well on the theme of this series of talks, right? So do you have some initial conditions, right? And then you actually look what are the consequences of this choice of the initial data in the asymptotic behavior of the field, right? As I said, so that there is a formal aspect of this, right? However, just mention that this class of spacetimes are actually covered by so if you have perturbation from Minkowski with this asymptotic decay, these results are actually covered by the theory developed by Lydia Vieri, right? So in fact, so these spacetimes actually with the developments actually do exist, right? So the only thing that one wouldn't actually need to do is somehow tie Lydia Vieri's result, right, with the gauge used by Helmut Friedrich and so on. But yeah, I see something that in principle could be done. Anyway, so just to wrap up this part, so I just want to ask the following: so why we care about this? Well, in particular because you see I've been repeatedly making use of results from stability questions, right? But in general, one would like to describe the gravitational waves or the radiation of strong field systems. So however, so my claim here, well, we have made use of stability results, right? Because these are somehow the simplest ones to look at, right? Where one has more tools at hand. However, the conclusions from the analysis of spatial infinity are in fact generic, right? So one actually can localize these questions near spatial infinity. So they are independent from the setup of stability. And the other thing that I want actually to elaborate in the next part of the talk is that Friedrich cylinder spatial infinity actually provides a framework to study somehow how certain objects defined spatial infinity at null infinity relate to initial data. Okay, so this is what I want to talk about in the remaining 15-20 minutes of this talk, and this is joint work with Marin Magdi, so former student of mine, and Kartik Prabhu, which I think is also here fielding the questions. And there is also a version of this for spin to fields earlier also with Marian. Okay, and then so this leads me to talk briefly about BMS charges. Yeah. Well, so it's, I think, well known for everybody in this audience, right? That so that the symmetry group of a non-infinity is the BMS, so Bondi-Messner-Sachs group. And so what are these asymptotic symmetries? So asymptotic symmetries are solutions to the asymptotic killing equation. So you generically, when you are space-time, you don't have a solution to the killing equations, right? But then within this geometric setup of null infinity, you can ask how much of the killing equations can I solve asymptotically, right? And then this gives you this BMS group, right? And then one can think of those BMS symmetries as transformations Cry, which preserve the structure, right? And then I have a slide delay, right? With the slides showing. The next slide. Okay. Okay, so why we care? Well, so there has been some interest in recent years coming mostly for the community of high energy physics, right? And then there is this triangle, right, which relates rotational memories of graviton theorems and asymptotic symmetries, and so these seems to be aspects of a common theme. Well, yes, somehow this is in particular what has sparkled my interest in, or renewed my interest in this particular topic. Now, in what I'm going to say later on, I will not look at the full EMS symmetries, but I will look only at subset which are super translations, which are reparametrization of the null generators of Scribe, right? So the way it works, so usually you have some adaptices of coordinates, so Bondi coordinates. I will say something a bit more about that. And then you have a parameter U, which somehow labels codes of Scribe, and then you can always reparameterize, right, by adding an arbitrary function on the sphere. And well, as you probably know, so in the discussion of asymptotics, one always makes use of a particular set of adaptive coordinates called the Newman-Penrose gauge, right? So basically, you are working with a null dyad where you have some vector when a Scri is chosen to align with the generator of non-infinity, and then somehow the other null direction somehow is aligned, at least a Scri, with the end points or the end of outgoing light cones. Right? So this is somehow the natural way of now reducing the complexity of the equation, right? So this gauge has three parts, as I said. So there's a particular choice of coordinates, a choice of frame, and also some extra conditions, right, that allows you to kill part of the connection, so kill certain Christoffel symbols, and then there is even a conformal freedom, and this can be used also to set certain parts of the connection to zero, and also the Ricci tensor. So, and then there is a whole like a cooking prescription, right, on how to construct these coordinates. Okay. Now, so what I'm interested in analyzing are the BMS charges associated to the super translation. Yeah. And then, so in this case, so these charges, right? So this is an asymptotic OR object defined in a scribe, right? And then this somehow the expression, right? The one likes to look at, right? So it's a quantity which is the integral, and you are integrating somehow the Weyl component, so the Coulomb component of the Weyl tensor, and plus an extra term that comes out from the shear tensor. So it has some information about somehow the gravitational radiation. And then you integrate this quantity against an arbitrary function on the sphere, which basically represents the super translations. And well, and then so this quantity, and then you like to, so you can evaluate this quantity in a particular cut of scribe, right? And you can also evaluate this somewhere else, right? Right, and in general, so these charges, well, they are not conserved, right? But they do satisfy a balanced law. Just waiting for the changes for the next slide. Okay, here we are. Right, so right, as I said, so the point is that there is a balanced law that relates the charges, saying this cut of scribe with the one here, and then so I just put this for non-infinite, future non-infinity, but then you can do the same for past non-infinity. And well, so in this line, well, so a natural question is to see what happens when you are taking the cut on non-infinity, on which are you evaluating the charges. You push it down to spatial infinity, to say that you push this to the critical sets that I was showing in the previous slides, right? And then you could ask whether these limits, and then you could also do the same in the past, right? To try to push these cuts to also to the critical set, for now in scribe minus. And the question is, on the which conditions these limits are well defined, in which cases these, and then if they are well defined, somehow how the value that you obtain in the past corresponds with the one in the future, right? And this has been called the matching problem, and a number of people have looked at this in different ways. So Strominger, Henault, Tracer, Kartik, Prabhu here, right? And some people I may also forgotten. So here, so what to do is just summarize a different take on this, in which make use of Friedrich's representation of spatial infinity, and to carry out this calculation of these limits, right? So the advantage of this is that so what we are, this approach, what we are doing is making assumptions which are controlled in terms of the initial data, right? And then ultimately the aim would be to rewrite these charges, the value of this charge of these limits, in terms of free data on the initial hypersurface. Okay. So for this, well, one has to make certain assumptions on the initial data, right? And then so you want to choose a class of data which is large enough so that the value of the charges is non-trivial, right? So if you have a class that's too restrictive, then the charges all of them are zero, so it's not very interesting. So fortunately, the literature, there's a result by Lan Huang, which tells you that well, so there is a large class of data for which you can evaluate charges in a non-trivial way, right? And so you can think of this as basically boosted initial data, right? So in particular, for the tree metric, in addition to the typical Schwarzschild term, there is also an extra term falling at the same order, which is an arbitrary function of the angular coordinates, and this term somehow encodes somehow, if you want, the boost. Right? So it's also interesting to note that this result also makes use of gluing techniques. And again, so we, as I said, so announced what I want to do is to make use of Friedrich's cylinder spatial infinity. So put in other words, so taking this data that I've shown before, so we want to evolve or solve formally the Einstein equations or conformal equations for that data, and look at the behavior, how this solution behaves along null infinity, right? And then the claim is that you do that here, then you have the solution of the field, gravitational field at this point, and then you can connect with whatever your limit of the BMS charges is on scribe plus. And then similarly, you could go to the past and then match with the the formula for the charges on prime minus. And then as everything is written in terms of initial data, you can compare. Right, so that's the general idea. Right, and then so it means that you have to compute a number of things. So you have to somehow solve for the Weyl tensor, the shear tensor, and also this n, right? It also has tied to the shear tensor. And then also you have to compute quantities associated to the gauge transformation relating somehow the Newman-Penrose setting in which somehow the equations, so the expression that I showed for the BMS charges is given, and somehow the framework which is used by Helmut Friedrich, right, in his setup. Right? And it's a very long calculation, and this was done by Mariam very bravely using computer algebra. And so the remarkable thing is that at least for the Weyl tensor, so at least for the order of these calculations, turns out that the Weyl tensor has this leading behavior, right, for the data that we have, right? So to say that to leading order actually allows an infinite number of harmonics, vertical harmonics, and then with some coefficients which depend on time. And then these coefficients can be computed explicitly. There are actually solutions to the Legendre equation, for which we will have an explicit solution. And this Legendre equation has always two parts. So we have two independent solutions. One is the Legendre polynomial, and the other one a Legendre function of the second kind, which always contains a logarithm there. Right, so that's to say that you have a bit which is singular and a part which is regular. Right, and then so these coefficients in front of the solution actually can be determined or fine-tuned, if you want, in terms of initial data. Right, and so remarkably, right, so the formula for the BMS charges that I showed also contains terms involving the shear tensor, but in fact, one actually can prove out of this very extensive computer calculation that in fact the shear tensor actually goes to zero as one approaches the critical sets. But in fact, so this means that the value of this, so you don't have to worry about these terms, right, when computing the charges. Also, basically, this says that at least this case, somehow the structure of the charges is formally the same as that for the spin to the field. Right, so and I mean, if you trace back, so what is the dependence of the initial data? Well, you see that these coefficients that appear in front of these Legendre functions actually are the multipolar decomposition of the function alpha in the data, which is associated to the to boost. And now, so just to conclude, so what one transpires from this analysis is that the solutions, so the charges, are generically not well defined, right? So you try to evaluate the charges for spacetime that include these Legendre functions at certain time. So the charges are not well defined. So you have to kill those parts that are associated to the Legendre functions. And one can see, right, that these are actually associated, so the regular solution associated to odd parity harmonics, and the ones that are even are the ones that give you the singular solution, so they're one that you have to kill. And then at least for the class of data that we are looking, so only BMS supertranslations with L even have non-trivial information. So somehow this actually differs from the case of linear case, right? So this is for somehow the experts. So differs to the linear case where there are actually non-trivial charges for even parity, right? And this has to do actually with the nature of the constraint equations in relativity. And as I said, so somehow the bottom line is that one can actually rewrite these BMS charges at the critical sets in terms of the multipolar structure of this function alpha. And somehow in this way, one can actually identify, establish the identification between the charges at the future and the past, right? So in particular, so we are doing this identification without actually requiring, not making use of this antipodal map, right? So the only thing that we are actually requiring here is a certain regularity for the charges to be well defined. Okay, so this is somehow the nice feature from this. Okay, and well, so this is somehow the main result, and I think is a nice example, right, of how this formalism of partial infinity can be used, right, to address somehow some important current questions regarding the structure of the relation of charges at future and past non-infinity. And somehow, so one, I think so this already somehow I guess establishes the usefulness of Friedrich's formalism, right? And also points out one of the main takeaway from this talk is that some of the standard assumptions are non-generic, right? So this is fine, right? So in the sense that well, so everybody is free to work with their assumption that they fit more natural and to define the system in the way they like the most, right? But then one should be careful, so at least one should be aware, right, that there is some assumptions may be non-generic. And I think the other point of view, which somehow ties with, I guess, the legacy of Ivan Shuket, is that as long as you are doing assumptions on free Cauchy data, somehow you're okay, right? So philosophically okay. So this is something where you actually have control, right? And I guess to wrap up this, so I think there is a point here which I want to stress, right? So in fairness, and because I think this is one of the main point of view, remaining things in the discussion is that this analysis that I described really relies on extensive use of certain asymptotic expansions, which are formal, right? But then, so you want to actually, so when you like to tie or make the relation between these expansions and actual solutions to the Einstein field equations more precise, and I mean rigorous, right? So this is something that one would like to do. And it may be that some of the methods devised by, say, Andras Bashi and Peter Hinz some years ago in also the study of, again, nonlinear stability of the Minkowski spacetime may give a way of doing this, right? But yeah, so this lies to be seen. And with this, well, I think it's time for me to finish. I'm slightly went over time, but thank you very much for your attention, and then happy to answer any questions if you have.
Thank you very much, Juan, for such a wonderful talk. And do we have any questions? I don't see anything in the chat.
Piotr raised a hand.
Yeah, Peter.
Hi, Juan. Yeah, very, very nice slides and very clear talk. So I think we last chatted about these things about half a year ago or something like that. Or so these calculations, is there something new that you've meanwhile obtained, or it's the status is pretty much the same as?
Well, I think that what is really new is that I think that the Helmut framework, right, on it really didn't work for this data for the land uses actually, right? It is actually, yes. So somehow Helmut's formalism, I think, was originally done, really didn't work for that one. So somehow you have to change slightly things so that you can allow for evolving data, which is boosted data, right? And this is where I think most of the work really went. Yes, and check that the transformations which were done by Helmut and Kanner would actually also work in this more general setting. Yes.
Okay, thank you. Another question. so I was confused by your comment about this anti-symmetry story, because so this antipodal map I thought just shows up naturally in the conformal completion framework. So, and you're saying you don't, you said something, you don't need it anymore or something like that. So I think it is there. Is it, or it's not, or it's actually
no? Yeah. So okay. So the statement would be the following. No? So say Strominger, right? For example, to make this identification or compare the charges, so it has to postulates.
Yeah, he does assume that period, but I mean, I think that this just comes out from the Penrose compactification, and so you don't have much choice. So
that's true, right? But there is, I think, there's an extra bit there of that you don't know what the regularity do you need for to do this identification, right?
Right.
So,
okay, I see. Okay.
Yeah. So this is this is, I think, the extra point. So, I agree, right, that the compactification by Penrose so somehow already give you the antipodal matching, but there is an extra ingredient more, right? That actually
yeah. Okay. I mean, it just the regularity might be completely off. Okay. Thanks a lot.
Yes.
Jahanur, can you please introduce us?
Yeah, so my question is that can your formalism can be this Friedrichs formalism can be applicable for time like infinity? I mean, what is your take on that? I mean, but because recently there's a work by Compare and Gralla, whether they can compare the Bondi-Sachs formalism to the Beck-Smith formalism, but they can compare it to the time like infinity also. I mean, do you have any comment? How can Friedrichs formalism can be promoted into the time like infinity case?
This is actually a very, very, very good question, which somehow is in my list of things that I would like. So I actually have no clue, but it really, I really feel that there should be a connection, right? So, we should somehow be able to adapt things, but I haven't had time or opportunity to look at that. But it's a very natural question to ask, right? So whether you have a structure there, yeah.
Or do you have any comment that how Beck-Smith formalism can be promoted? So Beck-Smith formalism is also valid at spatial infinity, and how can that be compared to Helmut Friedrich formalism?
Well, so that's right. So
that can give some clue.
Right? So you mean Weig and Schmidt?
Yeah, Weig and Schmidt.
Yes. So basically, yes. So basically, so this hyperboloid by Weig and Schmidt is basically the same hyperboloid that, or extension that the Ashtekar and Hansen make use, right? And then Ashtekar Romano, right? And then basically you can so you can show that this so there is a transformation, right? That relates a conformal transformation that takes the cylinder by Friedrich into Ashtekars or Weig's hyperboloid. Yes. So these are yes. Basically, you are just changing the somehow the conformal gauge, right, to pass from one to the other. Yes.
Okay, so there is a gauge transformation available to pass from Beck-Smith to Friedrich, right?
Yes, that's right. So, and this is in one paper I mentioned there. So basically, so it's given for well, obviously for Minkowski space-time, of course, but then the generic then later shown in that paper that you can do that for a larger class of space-time, which are not Minkowski.
Yeah, and my another question is that so in the first part of your talk, you mentioned that for asymptotically simple, but for lambda equals to 0 case, Peeling only hold, right? I mean,
yes.
What happens?
Yeah. So that was all lambda equal to 0 there.
Yeah, I mean, I understand if you put a cosmological constant, then your Weil scalar cannot be directional independent. I mean, what? But the follow-up should hold, right? I mean, if you just stay on the one light ray and ask for lambda equals lambda greater than 0 case, then Peeling should hold, right? I mean, what is your any comment on that?
Well, I mean, somehow so the setting is completely different, right? So
So that I understand. So if you change the light ray,
so you can yeah, so there are all these results also again by Helmut Friedrich, right, on say stability on of the Sitter spacetime, for example, and then you could really use that as a way of seeing so what is the expansion, the behavior, right, of the gravitational field or the Weyl tensor really on the timeline and space like conformal boundary, right? Yes. Yeah, so it can be worked out, right? So, and probably it has been done, but yeah, I don't have it on top of my mind.
Yeah, I mean, the thing is that, I mean, this Weyl scalar cannot be invariant if you change the direction of the light. But I guess while if you just stick on one light ray, then the peeling should hold for lambda non-zero case also, right?
Yes, right. So I think that the big difficult change, right, in the lambda non-zero, so
Yeah,
positive
that
case, that is less geometric, right? So there is not a natural
yes, I mean, in other ways, psi4 doesn't remain invariant. If you change different light
Right.
direction, then psi4 actually changes between psi 0 to. So that's why there is no invariant notion of psi4 or psi 0. But if you just fix to a specific light ray, then I think peeling should hold, right, for including lambda also.
No, I would know. I would have to have
Okay.
a bit more about that. But
Okay, thanks. That's all.
no, thank you.
Do we have any other questions? Okay, if okay, so questions have a question. So please, could you please?
Yeah, hi Juan.
Hi.
Since I'm questions, I should ask a question.
Yes, please.
How hard it is to do the, like you mentioned, and I mean I know this because we worked on this, the opposite parity case for the BMS charges, where half of the charges are zero because of the parity condition in the initial data assumption we're using. How difficult is it to get rid of it? I mean, I know we have to use different asymptotics for the initial data, but is that extremely difficult? I mean, this was extremely difficult, and Mariam did a very hard work calculation, but
I don't think it is. I think that so the in terms of calculations, I think so once the setup is done, so what Mariam has, I think the question is really how you identify data, right? That with this property, right? So I think that there is some amount of like a reverse engineering, I would say, somehow. So you would have to somehow add another piece of the data, right, that enters into the expressions somehow, right?
Yeah.
And I think that there is some amount of guesswork there, right? That one would have to figure out. But I think the calculation themselves, so the complexity is probably similar, right? It's more having the idea. In fact, also, in this project, right, that I was describing, so I think that it was to realize, right, I think what is the right data. I think this was, I think, the crucial step in some extent, right? And I think it's similar in that case.
Okay.
Yeah.
Okay, great. Thanks.
Thanks. Sumati?
Yeah, just very general question, but to do with the earlier part of your talk.
Yes.
I found it very intriguing, this, first of all, the fact that you get this generic non-smoothness in Spry.
Yes.
Also, the fact that you can relate it to the cotton tensor at I naught, I guess, right? I mean,
That's right.
So, do you have a, I mean, do you have some kind of physical understanding of that particular those sets of conditions? They're very nice geometrically, but is there sort of something that one doesn't pick up when one is looking at Spry plus or Spry minus and extra charge?
Okay.
Is it related to extra charges or something of that sort?
Okay, this is a good point. Somehow let's just move there, right, to show precisely this this point. Let me see. Yeah, so these are the slides. So, so it turns out, right, I didn't mention this here, but these conditions that you have here are also properties of static spacetimes. So in fact, static spacetimes satisfy the whole an infinite hierarchy of these conditions, right? So yes, right. And in fact, so here you are only so this property is somehow, yeah, as I said, so these these conditions with equal to 0 satisfied are satisfied for static solutions. So yeah, so you are requiring somehow your solution to be somehow static, almost like to a certain order, basically. Well, not really, right? Because you have radiation still, right? So, but it's a property that is shared by static solutions. Yes, I think this is I think what I could say. Yeah.
Okay.
Yeah, I mean, so there are extra conditions. So there are extra conditions to have something that is static as well, right? So which would kill off somehow this decay here, right? So that you don't have radiation, but
So it's sort of asymptotically more static than things that we would imagine to be asymptotically flat. There's
that's right.
sort of additional
Yes.
rigidity, if you like, at infinity.
Yeah.
And so it's all not true for things that are for Kerr and so on. It's not true. These conditions on the quantum tensor
Yeah.
at I naught. I mean, I'm just curious. Yeah.
I wouldn't know. I don't know. But something that is also remarkable, I mean, is that these conditions are actually they are conformally invariant, right? Yeah, yes, I think this is one an extra statement, right? So these conditions are actually conformally invariant, and right. So there's I guess an extra piece of information, and you would expect, right? Because yeah, so it actually has to be more a property of the conformal class of the initial metric rather than the actually particular choice that you are making.
Thank you. Yeah. Maybe one small, just very general question. When you say things are not smooth, what is the degree of smoothness that is violated? Is it just that it's do you know? I mean, the worst kind of thing is if it's simply continuous and you get extra cusps.
No.
Scribe class, then you have extra boundary terms we have to worry about in our action and so on. So just is it just a mild,
it's very yeah, it's very mild, right? So from the worst possible case, which is I guess like the one here, this is I think is so the third derivative of while is the one that is somehow so you can measure this in terms of the derivatives of this scale, but then sorry, the third derivative, the one that is into problems, right? So it's somehow so you really have a solution to the Einstein field equations, right? Ascribed, or the conformal equation ascribed. Yeah. Yeah. So it's yes, I you call this mild.
Okay.
Really.
Thank you. Yeah.
Do we have any other question? If not, let's thank Juan and thank both of the speakers of the session. And our next session will be at 7:45 p.m. Indian time, which will be like 3 hours 15 minutes from now, which will also be at 2:15 p.m. British time and 9:15 a.m. Eastern time in the US. So thank you very much, both of the speakers and all the participants for joining us. And we look forward to all of you to joining our next session as well. So thanks a lot. and have a
Bye.
nice time.
Bye.
Bye. And Juan, it has been a pleasure seeing you after a long time.
All right. Thank you. Likewise. Thank you very much. Yes, it's been a
Yes.
while. So
I should have said the talk was excellent. Thank you. It was will be a really nice resource to go back to. Thank you.
thank you very much. And we keep in touch. Okay. Bye bye.
Bye. See you around.